Hello everyone. So today we will be discussing regarding the higher order differential equations and how we can come up with the solution, meaning the general solution and the specific solution needed in order to solve this differential equation. So on our previous topics, we've only dealt with the order one. I mean, say we have uh, dy over dx is equal to 2 of x. So this is ordinary differential equation, right? But this time, we will be tackling regarding the higher order. So let's say we are now dealing with the order 2, order 3, and up to the nth order. Say we have now our equation like this. The second derivative of y with respect to x plus the derivative of y dx is equal to 2 of x. So this is not longer an ordinary differential equation, but this is an example of higher order differential equation because we are now uh, on the higher order, I mean the order 2, 3, 4, and above. Okay, so it is on the higher order. So one of the topic regarding this higher order differential equation is the what we call the linear homogeneous differential equation with constant coefficients. If we have this kind of equation, then we can solve for its general or specific solution according to this topic, or I mean according to this method. Okay, so but of course we need to determine what is linear homogeneous differential equations in higher order form with constant coefficients, right? Because in our previous topics we've also encountered linear differential equations as well as the homogeneous differential equations, but it is not in the higher order. So this time we will be having the uh, uh, solution with this kind of differential equation. So how can we say if our higher order is a linear homogeneous differential equation with constant coefficient? So any linear homogeneous differential equation with constant coefficients may be written in form like this. Say we have a constant coefficient a sub n uh, y raised to n, or this is the nth order, y to the nth order, plus the coefficient y n minus 1 plus that plus constant coefficient second derivative of y plus coefficient first derivative of y until such time that um, plus y is equal to 0. So note on this linear homogeneous differential equation, it is linear if the higher order linear DE, if this higher order linear is equal to 0. So if this linear differential equation is equal to 0, then it is said homogeneous. Okay, and by the way, coefficients A, this A is here, are real constant, meaning this is a real numbers that is uh, not equal to 0. So it has a value. Okay, so for example, we have a 3 double prime y plus 2 y prime plus y is equal to 0. Okay, so let's see if this is a linear homogeneous differential equation according to this definition. Okay, so we say that uh, any linear homogeneous differential equation is a linear equation equal to 0. So these terms here, we have, since we have a second derivative of y, then it is a higher order, considered as higher order. And also, since these derivatives here are raised only to 1, then we say that it is linear, right? Okay. If this y is raised to 2, I mean it is being squared, then it is not linear. Okay, the same definition of linearity as we have discussed before. Okay, so another. So the coefficients here are 3, 2, and of course our 1 here. Okay. These coefficients A are real constant, wherein it is not equal to 0. Okay. So again, we have a linear equation here that is equal to 0, then it is said homogeneous differential equation with constant coefficients. So any equation written on this form is a linear homogeneous differential equation. So another. So if we have a, say, mm, y, third derivative of y with respect of x minus 3 second derivative of y with respect to x is equal to 0. So let's see if this is a linear homogeneous differential equation. Okay, so check first for the linearity. So this is in order 3. We are in higher order, in order 3. Okay, and this is raised to 1. This is also raised to 1 and raised to 1. And if you can see, we only have coefficients, real constants, not equal to 0. Okay, so this term here is linear because there is also no dependent variable multiplied to this equation. Let's, for example, this term here we have a y multiplied by y, third derivative of y with respect to x. So since we have this dependent variable y here multiplied to this derivative, then this term now will no longer considered as linear, right? Recall on our previous examples of linearity. So since the equation has no y here, okay, then this is considered a linear equation. And plus, since this equation is equal to 0, then we can now say that this whole equation is a linear homogeneous differential equation with constant coefficients. Okay, so move forward, it can be written using the differential operator d in the form f of dy is equal to 0. So in this topic, it is important to use what we call the differential operator to write uh, these differential equations, these higher order differential equations. So this only means that this differential operator here, or this one, is only means that aside from writing like this, uh, we can use the differential operator d as substitute, okay, for the simplicity of our solution. So aside from using this, okay, we can transform all our differential derivatives in terms of the differential operator d. Okay, so how can we do that? Say for this one, if we write this, we have 3. Say our independent variable is also x, so we have dy second derivative minus 2 dy dx plus y is equal to 0. So how can we write that equation, that linear homogeneous differential equation, using the differential operator d? Simply, instead of writing this form, let's use d. So this one here, we have 3d, but it is raised to 2 because it is in the second derivative. Okay, so we transform this one into this one. Okay, minus 2, and then this form here is d plus, oh, since we only y here, then let's write only the coefficient plus 1. Okay, and that is uh, being quantified with y, okay, because of these terms, okay, it is equal to 0. Okay, so this is how we can write the this equation using the differential operator d. Okay, so how about for this one? Since we have a third derivative here, then we will use d cube minus 3, this is 3, right? D squared minus, uh, I forgot what is, I mean this is 10, d y is equal to 0. Okay, so instead of writing this, we convert these equations using the differential operator d. And also, we can transform this equation further into the what we call the auxiliary equation or the characteristic equation. This means that this auxiliary equation or characteristic equation here is an equation in D. So the auxiliary equation on these equations uh, is this one. Okay. So that is the equation in D. So the equivalent auxiliary equation or characteristic equation is 3d squared minus 2d plus 1. Okay. While on this side, we have this auxiliary equation as, I mean, this is also equal to 0. So we have d cubed minus 3d squared minus 10d is equal to 0. So this only means that this auxiliary equation is the equation in D. Okay, but on the other textbooks, they use M instead of D. So aside from using the letter D, let's use M so that it will be not confusing with the differential operator D. So the equation will looks like 3m squared minus 2m plus 1 is equal to 0. And for this side, for this equation, we have m cubed minus 3m squared minus 10m is equal to 0. So now this is our auxiliary equation with the use of letter M. Okay?